So good morning students. Today in this lecture video, we are going to discuss about operational amplifier. So first we will see the introduction about this operational amplifier. So an operational amplifier, or otherwise it is said to be op-amp, is an active circuit component designed to perform mathematical operations such as addition, subtraction, multiplication, division, differentiation, and integration. Similarly, common applications include voltage amplifications, which means amplitude and polarity will be changes. And similarly, it is used as an oscillator circuit, filter circuit, and instrumentation circuits. Op-amps are linear integrated circuit, which is widely used in analog electronic devices. And internally, an op-amp contains transistor, diode, resistor, and capacitors, which is integrated on a single semiconductor chip. So the device is packaged as a single functional circuit in 8-pin package. The important pin configurations of this operational amplifiers are pin 2, which is used as an inverting input, which means the positive of an input is 180-degree phase shift, which is in the output, which means the positive of the input will be as we get the negative in the output. This is said to be inverting input, and the non-inverting input, which is represented as pin 3. So in this non-inverting input, what we have given as an input, we will get that as an output without any phase difference. And similarly, in pin 6, we will get an output, that is, we will see the output from the pin 6. And for pin 7, we are applying the positive supply. As of pin 4, we are applying negative supply. And this is the normal or basic op-amp symbol. So in this basic op-amp symbol, we have 2 inputs and 1 output. And V plus V minus is said to be a biasing supply voltage. And as of pin 1 and 5, it is said to be offset null. So the circuit symbol is triangle and it has 2 inputs. Similarly, an input applied to non-inverting pin will appear with the same polarity as the output. Similarly, an input applied to the inverting pin will appear inverted at the output. Inverted means we have a phase shift of 180-degree. There are different types of input mode operation in this operational amplifier, and one is single-ended input, which means one input of the op-amp receives the input signal and the other input is connected to the ground. It is said to be single-ended input. So if the input to the inverting pin results in an output of opposite polarity. And next type of input mode is double-ended or differential input. So double-ended or differential input means we are applying input to both the inputs, producing an amplified output corresponding to the difference between 2 input voltages, that is V1 and V2. So both input applied with a difference of VD. So VD is mentioned as differential voltage or difference in voltage. So next type of operating mode is common mode operation. So in this common mode operation, the same input signal are applied to both the inputs. So the output ideally 0 because the operational amplifier amplifies the difference between the two inputs. So the basic operation of this operational amplifier will be divided into two sections. One is non-ideal operation and another one is ideal operation. So however, the ideal operation will be used throughout the analysis. So we are going to see about the operating principle of ideal operation. So first we will see what the non-ideal operation means and what are all the parameters we have in this operational amplifier. So in this non-ideal op-amp, we have some following characteristics. One is high open loop gain, which is mentioned as A, and the gain should be of the range 10 power 6. Similarly, high input impedance, because this input impedance will restrict the current flow which is applied from the input side. So, and hence the input resistance should be of very high, which will be in the range of 2 mega ohms. And similarly, we have low output resistance or low output impedance, which will be in the range of approximately 75 ohms. So the differential input voltage VD will be equal to V2 minus V1, where V1 and V2 are the voltages at the inverting and non-inverting terminal respectively. So similarly, these are the characteristics of ideal op-amp or ideal operational amplifier. So the first main characteristics is infinite open loop gain. So as of ideal operation amplifier, the gain will be infinite, and similarly the input resistance will also be maximum and it should be of infinite range, and similarly the output resistance will be approximately equal to 0 in this ideal operational amplifier. And for ideal op-amp, we need to consider the following cases, that is the current into both input pins should be 0. So this is for ideal operational case. So we need to consider both the input terminal currents, which is I1 and I2, should be equal to 0. And similarly, the voltage across the input terminals should also be 0. That is, the difference in voltage VD will be equal to V2 minus V1. This we have already seen. That is a difference in voltage. And that the difference in voltage should be of 0 for ideal op-amp. So if the condition is 0 means, then it will be considered that is V1 will be equal to V2. That is, both the terminal voltages will be unequal. So next we are going to see about inverting amplifier. So the circuit shows the inverting amplifier. So if you see here means we have positive terminal as well as negative terminal. So the supply is given to the negative terminal through resistance Ri, that is input resistance Ri, and we have a feedback resistance of Rf. Since the input is connected to negative terminal, the circuit is said to be inverting amplifier. And the non-inverting terminal, which is the positive terminal of this amplifier, is grounded. And hence, the circuit is said to be an inverting amplifier circuit. So from this inverting amplifier, our goal is to obtain the relation between the input voltage as well as the output voltage V0. So to get this relation, we are going to apply Kirchhoff current law at node 1. So at node 1 means at node 1, the currents I1 will be equal to I2 because of virtual grounding. So already we have discussed about the concept of virtual grounding. So virtual grounding means the node voltage at both the terminals, that is VA and VB, both the input terminals will be 0, which means will be equal. So according to this, to that virtual grounding method, the current I1 will be equal to I2, and similarly, with the help of Kirchhoff current law, we are going to find what is I1 and what is I2. So I1 will be the current flow through resistor R1, that is input resistor R1, and it is given as Vi minus V1 divided by R1. And similarly, I2 is the current which is flowing through the feedback resistor. So the current which is flow through feedback resistor is given as V1 minus V0 divided by Rf. So already I have said about the virtual grounding. According to that virtual grounding, so the terminal voltages V1 will be equal to V2, and since the V2 is grounded, so V1 is also equal to 0. So substitute the values of V1 and V2 as 0 in the above equation. We will get Vi divided by R1 will be equal to minus V0 divided by Rf. So from the above equation, we can able to find the output voltage. So the gain is given as output voltage divided by input voltage, and that will be equal to minus Rf by R1. So since the gain we have obtained here is in negative sign, and hence it is said to be an inverting amplifier. So next we are going to see about what is non-inverting amplifier. So similarly, in the non-inverting amplifier circuit, we will apply an input supply to the positive terminal of an operational amplifier, and the output terminal, that is the negative terminal, will be grounded through input resistor R1, and the feedback resistor Rf is connected from output to inverting input. So similarly, here also we are going to apply Kirchhoff current law at the inverting pin. So I1 equal to I2, and that will be equal to, that is we are going to find the current flow through resistor R1, and similarly current flow through resistor, that is feedback resistor, is I2. So from this, the current equation is minus V1 by R1, which will be equal to Vi minus V0 divided by Rf. So similarly, according to virtual grounding, V1 will be equal to Vi, since the positive terminal is connected to an input voltage Vi, and hence according to virtual grounding, it should be equal to V1, that is node voltage V1 and V2. So substitute this V1 value and V2 value in the above equation, we will get an output voltage of V0 equal to 1 plus Rf by R1 into Vi. From the output voltage, we have obtained the voltage gain. So already we have seen the voltage gain will be equal to output voltage by input voltage, and hence the gain which is obtained here is 1 plus Rf divided by R1. Since the gain is positive, and hence it is said to be non-inverting amplifier. So thank you, students. So the remaining topic we will discuss in the next class. So thank you all.